local global phenomenon in modular representation theory. It's already been a recurrent theme in, for example, Gabriel's talks. And so what is the point of view I will take today? And it's going to be, my talk today is going to be fairly disjoint from my talk on a Monday. So we are doing P representation theory. So we fixed a prime. And we are doing representation theory of finite groups, so therefore it is of course natural to expect that the P subgroups of G are going to play a role in this representation theory. And this is the point of view that I'm going to try and at least give an introduction to today. So P, as last time, will be a prime number. And for the most part today, I think possibly totally, I will just do things over the field of characteristic P. So I'm going to fix an algebraic closure and of Fp, and G will be a finite group. Okay, so mostly when I say block, I will mean a block of Kg, even though in the background it's good to remember that there are these blocks in characteristic 0. But for today, this is going to be at the forefront. Okay, and I'm going to take, because I want to exhibit sort of two local global phenomena. So I'm going to take a slightly more general point of view, not just blocks, but I want to work in the setting of G algebras. Okay, so let me just remind you, what is a G algebra? So a G algebra is, for me, is always finite dimensional. Put this talk in any case, finite dimensional K algebra. Along with an action of G by algebra automorphisms on A. Finite dimensional K algebra A, along with an action, so in other words, with a homomorphism, group homomorphism, G into the algebra automorphisms of K algebra automorphisms. Okay? And I'm just going to write this as because we want to think conjugation. So I will write this as G goes to the automorphism, which sends an element A to G acting on A in this way. Okay, so G belonging to G, A belonging to J. Okay, so A belonging to A, thank you. Okay, and actually I want to put this up one level. So there's a notion of an interior G algebra. Okay, so A, we'll say A is interior G algebra if it's a G algebra, but it's coming from inner, the G algebra structure is really coming from inner automorphisms. Okay, so if there exists a homomorphism, let me just call it I, from G into the group of invertible elements of A, such that for any G belonging to G and any A belonging to A, the action of G on A is simply by conjugation by this element. IG, I'm getting it all wrong here, IgA, Ig inverse. Okay, and not all G algebras are inner, and this being inner gives you sometimes very valuable information. Okay, so two examples, okay, and I'm going to try and keep, this will probably not work, but I'm going to try and keep these three boards for any generalities on G algebras. This board for one example, this board for the other example, but for sure this will go crazy very soon. But anyway, just to, if you see me jumping around a lot, you will see that this is why that's what I'm trying to do. Okay, so first example, maybe you call this the example, is you just take A to be the group algebra itself. Okay, and then this is an interior G algebra just via G goes to G. The most simple-minded way, of course, this is a G algebra. Okay, I don't have to say anything more. And then the action is by conjugation. Okay, so G acts by itself and therefore on its group algebra by conjugation. Okay, and the other thing to note is that if B is a block of Kg, then this interior G algebra structure is sort of descends to every block. So then this is also a group algebra just via now G. Well, if it goes to G inside Kg, then that's not good enough. You want it to fall inside the block, so you just multiply with the block. With the identity of the block. This is a central idempotent, so it's easy to check. This is this makes sense. This is okay, and so okay. So we have two algebras. These are both interior, and I just want to make a remark, even though I'm not going to be using that at all very much in my talk, but I think it's useful. That this is a very useful point of view. If you have any normal subgroup of G, then of course G acts on N by conjugation. Therefore, Kn is a G algebra just via conjugation. Okay, but in this situation, you will generally lose the fact of it being interior. Okay, and this can this is a complication. Say when you do Clifford theory, you want to descend, say even to simple groups or something. The fact that this is not interior action necessarily can be a problem. Okay, so not necessarily interior, but it's an important G algebra structure. Okay, so that's one class of group algebras, of G algebras and interior G algebras. And then there's another very important class. So if you take any finite dimensional Kg module, then this is an interior G algebra. And why? Well, just let G go to the invertible linear transformation that it is going to induce on V. Okay, so G goes to what do I want to say? No, let me write it like, how do I want to write this? G goes to, yes, sorry, excuse me. G goes to the linear transformation, which is that it's going to do. Why? Because, yeah, okay. Okay, so these are going to be my two examples of G algebras. Okay, now back to G algebras in general. Okay, so in this, what I write on the board, if I don't say anything about A, it's a G algebra. When I want to say, emphasize interior, that something depends on something being, or the algebra being interior, then I'll say it. Okay. Okay. So if you take any subgroup H of G, then of course you can look at the subset of fixed points. Okay. So this is all A belonging to A, such that HA is equal to A for every H belonging to H. Okay. And it's very easy to see. It's very easy exercise. That this is a subalgebra of A. It's invariant under the action of the normalizer in G of H. And by definition, every element of H acts trivially. So, well, you can even say this is a normalizer in G of H over H algebra. Okay? Now, if you have a subgroup of H, L, then of course it's easy to see that the fixed points of L are going to be larger than the fixed points of H, because it's less, it's a weaker condition. But we have a transfer or a trace map going the other direction. So we have a trace map from L to H, which goes from AL to AH. This is also totally, I would say it's almost like a ubiquitous construction. You just take A and you take the sum as X runs over a set of left coset representatives of H, sorry, writing it wrong, L in H, okay? And you will land, it's easy exercise to check that you will land inside the set of fixed points of H, and also that the image, so not hard at all to check that, of course, so this, getting it wrong, of AL, this is contained inside AH by definition, but it's also an ideal of AH, okay? Okay, so all totally elementary exercises here. Right, and now let me give a definition. So there are two notions, a sort of relative projectivity notion and a notion of locality or being local, which sort of interact with each other. And so I'll first give you the first one. So we say A is H projective, okay, if the trace map does everything you want. So if you go from trace H to G of AH, well, you're going to land in the fixed points of G itself, but if you get the whole guy as big as possible, then we say that this algebra A, which is G algebra, is H projective, okay? Now, let me just, on my example here, let me just explain, yes?
So when we're talking about ideals,
yeah,
you mean ideal in the usual sense and also group invariant?
No, it's not group invariant because this L may not be normal. So yeah, I just mean, and I think, should I say left ideal probably? No, it's a two-sided ideal. No, it's fine. Yeah, just ideal in the sense of ring theory. Yeah. Okay, so what's this got to do? Why am I saying projective here? So this is explained nicely if I use this example. Okay, so what does it mean for this in this particular case? Well, if A is our end KV, what does it mean? What is AH? Well, it's what we normally call, we would write the KH linear transformations of V, those that are invariant, okay? And then what does it mean to say, if I want to take the trace of an endomorphism, okay, V of something in here. So let me just write L to H of some element in AL, if it's some homomorphism phi like this. Well, what does it do to my vector, to this element of the vector space? This map we have seen last time. At least it's a piece of a map we saw already last time. Again, very, very classical. It just is this averaging procedure that we already saw last time, okay, which again comes, except now we are just doing the averaging over a set of coset representatives because we're not starting at the identity, okay? So this is for phi belonging to NKHV, NKLV, and V belonging to. Okay, and now here is the nice fact, also again not difficult fact, which is that examples are getting very difficult here for me to. Okay, so let me just write it like this. V is a projective Kg module if and only if A is projective with respect to the trivial subgroup. Okay, this is, and you can even ramp this up to saying V is relatively Kh projective as a module, namely that every short exact sequence that splits as a sequence of, when you restrict it to Kh, splits as a sequence of Kg modules by just replacing. Okay, so this is the reason why this notion is called projectivity. And this thing is, well, it is a part of a criterion which has a name, so I will write it. It's called Higman's criterion. Okay. Okay, so it's really measuring for you the notion of being projective, this context. Okay, now, just one remark. Okay. Very easy, again, if H, in general, contains a C log P subgroup, of G, then A is H projective because, well, let me just show you. You want to say that every element in AG is a trace of some element in AH, and that's easy because if you take an element A in AG, you just write it as A added to itself many times, divided, and you can divide because this number is P prime, and that is just the same as the trace from H to G of A, because every element of G acts trivially on A. Sorry, I wanted to divide still, yes, excuse me, thank you. Okay, so very, very easy. So this is telling you that if you want to reach a projectivity thing, you might as well stick to P subgroups, because everything above a P subgroup is necessarily, a C log P subgroup is going to give you, is a projective thing. Okay, so that's one notion. Okay, so this is sort of going maybe from, down to up in some sense. Now I want to go the other way. Okay, and sticking with my plan. Okay. Second definition. Well, before I give the definition, I want to write, sorry, let me just make some more notation. So again, I'm going to switch. I could stay with H, but I'm switching notation. Let P be a subgroup of G. And now I'm going to define, let me write this, A less than P to P to be the sums of all the traces from Q to P where I allow myself only proper subgroups. Okay? So each of these, we saw each of these is an ideal. Okay? So I'm taking a sum of ideals inside AP. Okay? And now this one, I can be sure, is a normalizer in G of P invariant ideal of AP, because I'm allowing all proper subgroups, so conjugation is not going to affect this ideal. Okay, and then I'm going to define. So now I can take the quotient by this ideal, and I'll get a normalizer in G of P, mod P, algebra. Okay, so here's like this local global happening, right? So we started with a G algebra, and we are now getting to a normalizer in G of P algebra, okay? And here's the definition. I'm going to say A is P local if A of P is not 0. Okay? I should say, let me put this in quotes because this is just a definition I've made up for this talk. Okay? I haven't really seen it anywhere, but okay. So again, note sort of the complementary fact that if A is P local, then P has to be a P group. Again, it's easy to see. Just the same argument we had before. Okay,
P wasn't a C-log P group?
No, it was just, yeah, it was just.
P is H.
Yeah, P could be H, yeah, but it somehow just feels, yeah, wrong, so, yeah. Okay.
So P local, H local.
The H local could be H local, yeah, except, yeah.
It's only.
Yes, yeah, it's only, yeah, and. Okay, and so now let me use this example to say what, I mean, to give some, why P local, why am I calling this P local? So let's look at this example here, okay, and see what, so I'm going to let here P be a P subgroup now. I really want it to be a P subgroup, because I want for the arithmetic to work out. Okay, so now, this algebra, G is acting by conjugation, okay, on G. So the crucial thing about this algebra now is that A so this is definitely not true for general G algebras, but this particular G algebra has a P invariant K basis, okay? Namely the group elements themselves. So P is acting by conjugation. Okay, so now if you think a little bit about what that means, what is AP going to be? Okay, it just requires a little bit of thought. Okay, this is going to be the K span of P class sums, right? You take an element of G, of your basis, okay, and you want it to become invariant, so you have to add all its P conjugates in there, and you take the sum of that, and you'll get all of them. Okay, I'm going quite quick, but it's all quite easy exercises, these things, okay? What is this ideal A less than P to P? And here I'm using the fact that now the characteristic is P and P is a P group. This is the K span of P class sums. This requires a bit of thought, but of size greater than 1. Okay? So if you want to quotient out, if you quotient out all the class sums of size greater than 1 from all class sums, you're going to be left with class sums of size 1, okay? And so what is that telling you? That is just the centralizer in G of P, okay? So from here pops out that A of P is just in a natural way, just isomorphic to the group algebra of the centralizer in G of P, and this is as in GP, P algebras. And the also very easy thing that comes out of this is that if you want to interpret the quotient map, the canonical map from AP onto this quotient, okay, so the map, the surjection from AP to A of P in this case becomes under this identification So this very important homomorphism. It's a Brouwer homomorphism, okay? Brouwer P from, I'm going to write now, I want to put the group, the actual algebra back in the picture, okay? From the fixed point algebra of Kg to the group algebra of the centralizer in G of P, and this map is really very easy. So you write every element of Kg as a linear combination of group elements. And what does the Brouwer homomorphism do to that? It just sends it, you just do the most easy-minded thing. You just chuck away everything that's outside the centralizer. Okay? And this is called the Brouwer homomorphism. Pardon? What is who? Oh, no, sorry. That was a remark. There's no more any normal subgroup. Yeah, that was just to, it was to give you an example, natural example of a non-interior G algebra. So no more n, just, forget that. Okay. N equals G, there's no,
So the local case, P local case is when the centralizer P is non-trivial.
Which is always the case because P has a center, in fact, it's, even if P was, it didn't have a non-trivial center, it has, identity is always in there. So you would get K at the very least, but you'll always get something more. So okay, what this is saying is, of course, the group algebra is P local for any P subgroup P. So that's not very interesting, okay, as you just pointed out. Thanks for actually pointing out. In terms of that definition of P local I gave you, I haven't said anything, But when it comes to blocks, it becomes important, okay? So remember, a block, the Kg is decomposing as a product of blocks, okay? All of this is working very well with the block decomposition, okay? So what will happen if instead of taking the whole Kg, I take a piece, namely the block, I'm going to land inside here, but I may disappear totally, okay? And if I don't, then I am P local, okay? So what's happening? Oh, right. I forgot to erase that. This is not working, that technique of middle top.
Well, you have to erase sometimes.
No, erasing is okay, but I thought I could have. That's what I did. Okay, anyway, whatever. So, okay. Right. So being P local for group is not, the whole group algebra is not interesting because for every P subgroup, the group algebra is P local. But now if you take B is a block of Kg, then either if you apply this Brouwer homomorphism to the P of to B, you go away. Then you're not, the block was not P local, or BP is a piece of the group algebra of KCGP of CGP. So it's a product of blocks of KCGP. So what is happening here is, so just to sum up, for every block, okay, and for some P subgroups of that block, we have a nice way, sort of easy way of associating to that block, which now we may think of as our global object, okay. We have associated a subset of blocks of this local subgroup, centralizer in G of P. Okay, I'm going to come back to this this point of view maybe in my next lecture more about this, what is this product of blocks actually mean, what's going on here. But right now the only message I want you to take away is that For certain subgroups, P subgroups, if you do the Brauer construction, you get nothing. And so that P subgroup is not interesting for that block. Okay? And for others, you get something, and what you get is always a nice piece of the centralizer in G of P.
Is it understood which P groups give nothing?
Yes, I mean, well, understood is, it's a very dangerous word.
It's studied.
It is intensively studied, I could say, yeah. Which, yes, I mean, that's, and I will hopefully be able to say something about that in the lectures. Okay, so now,
Middle first. You're on the middle. Yeah.
oh, this is the middle?
Yeah.
Yeah, okay. Now, theorem. And I think in the generality of G algebras, this is due to Puch, but these ideas have been there from the beginning of modular representation theory. So this is just one way of formalizing them. And so what is the theorem? Okay, before let me just say, suppose A, and then I will define this, is a primitive G algebra. So what that means is that, i.e., the identity of A is the only idempotent in the fixed points of G. Okay, this doesn't. If you see it like this, it is not very illuminating, but it's saying it's sort of indecomposable in some kind of way, okay, as small as possible. But just to remember here, we can forget about this primitive word, block algebras. So if B is a block, then B is in fact a primitive G algebra. And in this example, when is A is primitive, if and only if M is an indecomposable module. V. It was V. It is still V. It's always going to be. It's going to remain V. Okay. So again, this is easy. Maybe Fitting's lemma or something. That's what I'm saying. Okay. So in the two examples that we're interested in, this theorem applies, and it says, okay. So let me give several statements and let P. So let me fix. And I'm just going to stick to P subgroups because that's all I need, really. And you say P is minimal with respect to A being P projective. So this is the first main, really, this is the punchline equivalence. So P is minimal with respect to A being P projective if and only if P is maximal with respect to A being P local. Okay, so this one you have to do a little bit of work. Okay, and so it's this, like I was saying, you work somehow from the top and from the bottom, and then where the two meet is where you want to land. Okay, and so I'm just going to, I know it's not good practice, but I'm going to use the theorem itself to give the definition. So if P satisfies these two equivalent conditions, so if P satisfies above, then P is called a defect group. of A. Okay, and let me just, because it already came up also in Gabriel's talk, he used the word vertex. Okay, so for those who have heard about vertices or sources or of indecomposable modules, in the situation of this example, a defect group of A is a vertex of V. Okay, so note, in this example, if V indecomposable, so you can apply, then P is a defect group of B is really the same of A is the same thing as saying that P is a vertex of B. Okay, so somehow we're going to get, well, the theory of vertices and sources also out of this point of view. Okay, so this is well, when you are working in the situation of block, then this is what we call defect groups of the block. Okay, that's one way. And then second statement I want to make is that, again, this is not obvious. You need to do a bit of work. Defect groups of A a G conjugacy class of P subgroups of G. So this is where you see some, again, shadow of, like, again, group theory coming in. It's really sort of generalizing the fact that C of P subgroups of a finite group are all conjugate inside G. Okay, and then I will put another statement, which is actually very important. So that's why I will put it. I may not be able to. Yes, so now that you asking if, that's right, in every group has a block whose defect group is the C of subgroups. And let me just put that here. So if B is the principal block, then the defect groups of B are the, so then defect groups of B are C of B subgroups. Of G. Okay, so, right, and now the third. Third part, which is actually sort of making this a bit more subtle. And this is in terms of idempotence. So if this, the third statement, if it looks too complicated, you could more or less forget about it for the time being. Okay. So suppose P is a defect group. P a defect group of A. So that means, remember that it means that you can get everything in AG as a relative trace from AP. Okay, so now this is going to just refine that condition a bit more. Okay, it will tell you more precisely which part of AP you need. Okay, so there exists then a primitive idempotent I in this algebra AP, okay, which is unique up to conjugacy in the group of units of AP, okay, such that in fact you can get AG so you don't need to trace up from all of P, from all of AP, but you can only only have to trace up from the ideal generated by this idempotent I. Okay. The fact that there is the existence of I is again is the easier part. It's this uniqueness up to conjugacy in AP star that is requires a bit more work. Okay. It's ugly. I'm going to erase it. Okay. I hope I'm. Yeah, I was trying to make this smooth, so I hope I'm not making too many mistakes. Yes, I knew I would make a mistake here. What did? Ah, yeah. Oh, yes. How should I fix this? I knew at this point I would say something. And I don't want to leave it up here. Right, unique up to. Yeah, and let me just say this again vaguely. Thank you. And conjugation by NGP such that this happens. Okay? Sorry, yes. Of course, that's very important. Yeah. Okay. And this idempotent as above, I is called a source idempotent of A. Okay, well, now I made all this fuss about introducing this this idempotent, given you the wrong characterization. But so why did I want to do it? Well, one of the reasons I wanted to do it was that if A is interior, and I is a source idempotent, then A and IAI are Morita equivalent. K algebras. Okay? So now when you truncate an idempotent with an algebra with an idempotent, you get smaller. Okay? And what I wanted to emphasize with this part 4 was here that the local theory, okay, is somehow giving you a natural candidate of a smaller algebra, okay, which is Morita equivalent to the algebra you began with. Okay? And in some sense, one could say that in the context of block theory, this, instead of working with basic algebras like we did last time, if you want to keep the group into the picture, this is the right sort of replacement for the basic algebra in the context of blocks. Okay, but I don't know if I'm going to come back really to this. It depends on the time. Let me just fill in this picture here. This is more about vocabulary. So vertices and sources. So does this thing give you sources as well? Yeah, the sources are hidden in there. So if I, in this situation of endomorphisms of a module, if I is a source idempotent, of A with respect to the vertex P, then just look at the module that you started with V, multiply it with I, okay? Then this is an indecomposable KP module. Okay, and this is what's called the source. Okay, just for those who have vaguely heard about vertices and sources. And okay, so now let me, for the next few minutes, sort of concentrate on a block of a finite group algebra. We have seen that every block has associated to it a conjugacy class of P subgroups of G, and which satisfy these two conditions. So why is this an important notion? So I will just say a few things now about the groups. Thank you. Little board. Okay, so from now on, B as just let me write this block of KG, P defect group of B. Okay, first of all, to tie back with Monday's lecture. So now just facts. The order of P is just P to the defect of B, which the defect was this number that I defined in my last. So where D of B is defect.
Is there any P subgroups then? What is P?
Defect group.
Sorry.
Okay. And now depending on, so these are facts about the defect group. What did I write? Yes.
P is the defect group of B. The next line.
Of B. Yes, yeah, thank you. Okay, so now there's various ways to think about this, alternative ways to think about this defect, about these defect groups P. Let me give, if you like derived categories, let me give a definition or characterization or in terms of derived categories. So P is minimal amongst P subgroups of G such that the restriction functor from G to P of the derived bounded category of the module of the module category of B to the same for the group algebra of KP, this is faithful. I'm not going to say much about this. In fact, I'm not going to say anything at all about this definition. It's just to say that this immediately gives you a structural way, if you like, of thinking about defect groups. Okay, let me give one. Maybe there are many characterizations. Okay, and I have to say that actually to show that they are all characterizing the same class of subgroups is not at all an easy task, but it's all well known. Let me give a maximality. Yeah, so you could also write it in terms of maximality is maximal amongst P subgroups. Don't need really P subgroups here, but it could be any groups, but such that which one do I want? Such that Kp is isomorphic to a summand of B as Kp bimodules. Okay, there's several more, but I don't want to keep on going. I could spend the whole lecture doing that, but that's not my point here.
So the last 2 points are saying the characterizations of these.
Yeah.
The first point is not a characterization. This is just a consequence.
That's just a fact. Yeah, that's just a fact. Yes, but these two are characterizations. Okay, and just some more. Well, facts which are not at all easy, but they just get one line in this lecture. So why is the defect groups important? So first of all, let me just say the representation type of B, okay, is the same as the representation type of Kp, for those who used to thinking about representation type. P is cyclic. Yeah, exactly, tame wild, exactly, in the tame wild, finite tame wild type. P is 1 if and only if B is a matrix algebra. Okay, P is cyclic, so this came up last time, if and only if B is Morita equivalent to a Brouwer tree algebra. Okay, and just to give you, so these are all, I mean, this fact is not maybe that difficult, but this, of course, is very difficult. This is also not totally easy, I suppose.
Did Brouwer know about Morita equivalence?
No, he stayed away from modules. He didn't, but he developed the character theory of all blocks with. I mean, I would like to say actually probably knew, but he just didn't use that language. Okay, and I'm just going to give you another result. This just to give you a flavor of why we are so interested in these defect groups. And this is saying, now if I consider B and B prime blocks of two symmetric groups, respectively, so just consider the family of symmetric groups and look in blocks there. Then the blocks are derived equivalent if and only if B and B prime have isomorphic defect groups. This is a result of Chuang and Ruquier from maybe 15 years ago now. Okay, so this is, I like to always put this up just to illustrate the power of of how much the nature of this P is influencing the representation theory. Okay, only 5 minutes, so let me I want to state the Brouwer correspondence and then one conjecture, okay, and then I'll stop there. No?
Use the one in front of you. Just don't do anything. Use the
Okay, yeah, use the one in front of me. Yes, yes. No. This Chuang-Rukie is much stronger. So it's like a global sort of result. Yeah, no, it's not a global local result. Okay, and I'm sorry I haven't put names here because that would take a long time. So, but these are all celebrated theorems, so I think you can. Okay, so now Brouwer's first main theorem. So that's now easy to state from all the stuff that we have put up. So B block of Kg, P a defect group, of B, then, so there exists a unique block, let me call it, say, B star, of the normalizer in G of P such that so you can apply the Brouwer construction from G to centralizer in G of P. You can also apply the Brouwer construction. Everybody's looking very B star. What is the total nonsense? Excuse me. Again, C, P. I'm sorry. When I look when I start looking at the clock, and I see it's reaching its end, I start getting even more nervous. Sorry. Yeah. Is this okay now? Yeah. So you're applying the Brouwer homomorphism, which is away from going from G to centralize in G of P. You apply it to G, and you apply it to this local subgroup normalize in G of P. And for every block B, which has P as a defect group, there's going to be a unique block of the normalizer, which picks out the same piece of the centralizer. And then B going to B star is a bijection, then between the set of blocks of Kg with defect group P and the set of blocks of the normalizer in G of P with defect group P. And here, let me now put the conjecture. This is Brouwer's abelian defect group conjecture, which says that if B and B star as above, if P is abelian, then dB of mod B is the same as dB of mod So a block B, and this B star is called the Brouwer correspondent. If you are in the situation where your defect group happens to be abelian, then these the derived categories of these blocks should be equivalent. And let me just end by saying, to tie it a little bit with the first lecture of the morning, in this case where P is abelian, this conjecture, Brouwer's conjecture, will imply Mackay, and because characters, but maybe I should say the version of this conjecture over O now, yeah, would imply Mackay conjecture and also Alprin weight conjecture. And so in this special case where the defect groups are abelian, for these wonderful numerical conjectures, there is at least a conjectural explanation. Okay. Okay, thank you.
Question? So in this Brouet conjecture, is there a map that we know?
So not in general, but so they are sort of souped, like they're souped up versions of this conjecture, and that there should be a particular type of derived equivalence. But in the special case of finite groups of Lie type, where a lot of work is going on around this conjecture, there is a much more precise formulation by Brouet, which says that in fact the derived equivalence should come, in many cases, from the complexes behind the L-adic cohomology. So they themselves should be inducing the derived equivalence. So that is extremely precise. But in general, there's no.
Are the blocks of Sn known or describable?
Oh, totally. So that is already that is what's called the Nakayama conjecture. Okay, and it's totally combinatorial. Two characters lie in the same P block if the labeling partitions have the same P core. And then you can describe all the defect groups, everything smooth. Yeah. Yeah.
For the same with the blocks of Sn, is there anything like that true for general groups? Like,
well, so I mean, the thing is, there's this internal combinatorics, right? I mean, you have a natural way of embedding Sm inside Sn when m is less than n. And therefore, you have this wonderful induction restriction, okay, between module categories. And then you can work that. Okay, and that's, I mean, so you work it and at a very high level, and then you get to this result. So really, I should say that, I mean, one of the things that we have for general finite groups and you want to compare module categories of different blocks of different finite groups, I mean, the functors that we have available, say I would say before this stuff coming from Lustig's theory, the only functors we had were induction and restriction. Okay, you don't really understand, I mean, the category of bimodules is absolutely humongous, okay? But there are only, there's only one bimodule that we actually really know how to do anything with, and that's induction restriction. And so in various special situations, that induction restriction or certain summand of it, there's enough outside information that you can use that. In some sense, I would say that this sort of newer approach for the finite groups of Lie type and non-describing characteristic, that's giving you new functors that are not directly related to induction restriction in any way, or at least don't seem to be. But yeah.
So for the representation type of B and also the KP,
Yeah.
and they're the same. Are there any kind of correspondences of indecomposables?
So actually, I ran out of time, but this example board was going to do that. So there is this very classical green correspondence, okay, which not directly with the defect group, but if you're working module by module, you can do it at the level of vertices. So you take modules of G with vertex Q, and you take modules of normalizer in G of Q with vertex Q, and you have nice. Yeah. And that, okay, yeah. And we use that a lot for conjectures like this.